Uh-oh, did I forget to send out the invitations? All right, hold on. Let me take care of that right now.
No problem.
Okay. Jesus, I knew this would happen sooner or later.
Makes it interesting.
Yeah, I guess it just slipped through the cracks. Hold on 1 second. All right. All right, we'll give them all a minute to get here. Yeah, I didn't realize it till just now. I guess I forgot.
No problem. Sounds good.
Okay. All right, people are coming in. Okay. All right. Well, we'll get started very slowly because I know that I screwed up and I forgot to send out the invitations. So I'm hoping that everyone will get here in a couple of minutes. But what was still needed to be done was we were not completely done with the sample midterm, which is right here. Now, by the way, I did go ahead and post the actual second midterm on Moodle. Let's go take a quick visit to Moodle. All right, so it's I put it. I decided there's no point in waiting. I just put it there. It's right here at the bottom of this January 4th through 10th group, so you can start working on it anytime you feel like it. The solutions that we did yesterday are right here, but today we still have a couple more to do, and also chapter 10 is in here now, which will probably start today. We're not done with 9, but we're getting very close to the end. So all right, so that's all taken care of. We also have the solutions to chapters 3 and 5 in here. And then, of course, last night you should have handed in 6 and 7, which is good. And then by Wednesday night, you should have the first midterm, and then everybody will be caught up. All right, so let's get this going. And so we're still, we were done with 5. That's right. We still have to do 6 and 7. All right. So now the interesting thing about 6 is that we're looking at a normal distribution problem. How can you tell? Because it actually says the words normally distributed. And this time, though, it's not the standard normal, unlike this problem here, where clearly these are all the standard normal random variable, which means that the mean is 0 and the standard deviation is 1. Here, it could be anything. So it's 12% for the mean and 30% for the standard deviation. So we're going to call this X, let X represent the returns to this pension fund's global growth fund. And they're normal with a mean of 12%, which I'll write as 0.12, and a standard deviation of 0.3. So, of course, that means it's not standard normal. It's just a normal probability distribution. Now, if you are planning on using the tables, then you'll need to use this conversion formula. Sorry, X minus mu over sigma, which will enable us to convert these questions into standard or z-scores. Okay, so for example, in the first case, we have the probability that X is less than or equal to 12%. All right, now, if you can visualize, this is the distribution for X. 12% is the mean. And so what this formula here will enable us to do is convert this into a standard normal form. And if you use this formula, you'll see that if you apply it right here, we subtract the mean, which is 12%, and divide by the standard deviation of 0.30. And that gives us the probability that z is less than or equal to 0. And so these are the two probabilities on the two curves that we're looking at. Now, this one we don't really need the charts for, because you know that based on the properties of the normal distribution, the probability of being below the mean or less than the mean is 0.5. Okay, so in other words, you could stop right there and just say the probability is 0.5, and you'd be correct. But if you went to the table, the normal table, let me go get that normal table open. Let's see. We'll get the positive table. All right, so there it is right there. In other words, 0.00 is the actual mean of this distribution. Everything to the left of that point has a probability or area of 0.5. Okay, so on this graph, that would just, of course, be everything below 0. And that, according to the chart, is 0.5. All right, so that one's done. Now, if you're going to use the calculator, of course, what you have to do is go to second VARS. And when you get to that, you're going to choose normal CDF. Okay. And once you've done that, it's going to ask you for 4 pieces of information. Lower, which in this case is negative infinity. Now, remember, in this calculator, that's expressed as minus E99. Okay, and I'll remind you again that this is entered as negative second comma 99. Okay, the upper limit would be 0. Actually, no. I'll tell you what we should probably do here. Instead of using the standard normal, what you can do is, you don't need this conversion at all if you're using your calculator. You can use the original values for X. So in other words, we may as well take advantage of that by just leaving the upper limit as 12%, and then the mean would be 12, and then the standard deviation is 0.30. Okay, so you can use 0 and 1 here, but because the calculator will get the same answer either way, you may as well just leave the original data in there. And you'll notice when you do go through all these steps that you're going to get something which is not exactly 0.5, and that's because of the rounding of negative infinity. Okay, you'll notice this time it's 0.5000005. It's almost 5, but you can just round it to 0.5. Okay, because that is the exact value. Okay, so anyway, so that's the first one. Now the rest of them you can do the exact same way. Either you convert to a standard normal form and then use the table, or you can throw these numbers directly into your calculator. Okay, so then for part B, more than 27%. So what we're looking for again is some location under this curve. This is the original data. This is the actual distribution of the returns. And under the standard normal curve, we have 0 here. Let's fix that up a little. And that corresponds to 0. So if you applied this formula, so again, you're subtracting 12 and you're dividing by 0.30 to get to this z-score. So the probability of z is greater than or equal to 0.27 minus 0.12 over 0.30, or this is the probability that z exceeds 0.5 actually. Okay, so in other words, 27 here corresponds to 0.5 down here. This is x, by the way, and this is z. Okay, so if we look in the chart, now of course, when you look in the chart, it doesn't actually have the probability that we need because it's all less than or equal to. So don't forget. So based on the chart, we can compute this probability as, okay, the probability that Z is greater than or equal to 0.5 is equal to 1 minus the probability that it's less than or equal to 0.5. All right, and that's of course because the entire area under this curve has to add up to 1. And so then we can go directly to the chart to look for the 0.5. And let's do that right now. We don't need this anymore. So that's 0.5 combined with 0.00. Okay, so remember, this is just going to be written as 0.5 plus 0.00. And at their intersection, you'll find 0.6915. So our answer will be 1 minus 0.6915, which is 0.3085. All right, so the tail area here that we're looking for in both cases is 0.3085. So that's the final solution. Now, of course, we can come up with this with our calculator. Let's go repeat these steps, except now, of course, the numbers are a little different. So you're looking at a range from 27% up to positive infinity, which the calculator will show you on the screen as E99. Okay, now that's the same thing without the negative sign. Okay, so when you plug in those numbers, you should get the same thing, except for maybe for some trivial rounding differences. So you plug in the numbers, and what do you get? All right, let's try that. We got 0.27 up to positive infinity with the same mean and standard deviation, and yeah, 30854 something. So that's fine. You should usually round these to 4 places anyway. All right. So far so good. Is everyone getting caught up? Excellent. So I see almost everyone's here. I apologize for the screw up with the invitation. I just forgot, and I didn't realize it until the last second. But anyway, let's carry on. What's number 3? Less than negative 3%. All right, so it's, it's the same basic setup. So what we're looking for then of course, that means you lost money, which is not happy. This is not happy territory down here. But if your return is a loss of 3% or even worse, what's the likelihood of that happening? That's what we're about to find out. So that's the X distribution. This is Z. This is 0. So what we're trying to figure out is what is the equivalent Z score for X being less than negative 3. Okay, so we need our conversion. Whoops, no, we don't need it that big. That was scary. Okay, so here's what we have to do. Of course, we're going to apply this formula. Which means that we now are essentially doing the same thing as saying, what's the probability that Z is less than or equal to negative 0.03 minus 0.12 over 0.30. So this is less than or equal to negative 0.5. Now, here's an interesting result. The previous question asked us to find the probability that z is above positive 0.5. This one, we're looking at the area below negative 0.5. So if you look at these carefully, you'll see now, of course, the drawing is not perfect, but because of the symmetry of the distribution, the probability that z is less than or equal to negative 0.5 equals the probability that it's greater than or equal to 0.5, which in turn, as we already know, equals 3085. So you actually don't really even need to go to the charts again because of this symmetry property, which is very, very helpful in many cases. So your final answer is 0.3085. Just like up here in part B. But if you didn't notice that, that's fine. We'll go to our table or chart and we'll look for the probability of negative 0.5, and that will give us the correct answer as well. We'll go to the negative table, and because this is less than or equal to, we will find it right on the table. Okay, here we go. We have to open up the negative table. Negative 0.5 combined with 0.00 is right here. And to nobody's surprise, you can see that it is in fact 0.3085. Okay, so we'll go back here. And then of course, if again, you didn't notice this and you use the calculator, let's see what you would have gotten. Well, we know what you would have gotten, but let's just demonstrate it. So this time, remember, we're looking for less than or equal to negative 0.03. So we've got negative infinity. And then we have up to positive, well, negative 0.03. And so when you plug in those numbers, let's see how that turns out. Negative infinity up to negative 0.03 will give me a probability of 0.3085 exactly. All right. So far, actually, we're getting pretty good at this, aren't we? Yes, we are. Okay. Now, by the way, you do not have to draw all these graphs to give me your solution. All I need is just do one of two things. You convert to Z and then use the table, or just show me what you did on your calculator. And then that will be quite sufficient. You can draw the graphs if you want to, and it might help you visualize what you're doing, but it's not mandatory. Okay. So anyway, what's next? D. Here we go. Some in-betweeners. Between negative 0.18 and positive 42%. So this is a pretty scary little stock here. There's a roughly 31% chance that you're going to lose more than 3% of your money if you invest in it. So that's something to think about. But anyway, between 18 and 42, negative 18 and 0.42. What else coming? All right, so on the original distribution, so this is a huge area that we're looking at here. That covers a wide range of possibilities. Okay, so what we need to do is figure out what z-scores these correspond to with our favorite formula. All right, so remember, we're going to use this formula as always, unless you're using the calculator, and then you don't, of course, need it. But to use the tables or charts, first things first, this is what we're actually looking for. Okay, so when we apply that conversion factor or formula, okay, so that works out to be wow, it's turning out fairly nicely. We're looking at the area between negative and positive 1. Okay, now I didn't draw this terribly well. That area doesn't really, I made it look like this covers like 90% of the distribution. It doesn't, it's like 2/3. But that's right, as long as we can visualize what we're trying to calculate. Now, based on the table then, this probability can be calculated as the difference between these two probabilities. And both of these are less than or equal to probabilities, which makes things a lot easier for us. So also keep in mind that what you're actually doing, let me just fill these in, is in order to look things up in that table, you do need 2 decimal places. All right, so let's take a look. Now, some of these, after a while, you start to have them memorized. Like the 1, which we've seen many times before, you'll recognize it right away and say, oh, that's right. I remember seeing that. 1.0 right here has a probability of 8413. Okay, so let's fill that in. And then we subtract the negative version of that. -1 is right about here. 1587. So the final answer is the difference between those two, 0.8413 minus 0.1587, which is 0.6826. Okay, so the total area about 68.26% chance of getting your returns in that interval somewhere. All right, and again, if we're going to use the calculator, all we need is to know that it's between negative 8.18 and positive 0.42. And that turned out to be 0.6826. Very good. And then I think there's one more. Yes, another in-betweener. Okay, so what are we trying to figure out here? All right. And of course, that's from the original or X distribution. And now we want to convert it into the standard normal form. Okay, so let's apply our formula here. And so we've got the probability that X is between these two values is equivalent to Z being between these two values. Okay. All right. All right. So it's between, yeah, and again, I didn't really draw it that well, but you get the idea. And of course, because it's in between, what we're going to have to do in order to look this up in the charts or tables is rewrite it as Z less than or equal to 0.5 minus less than or equal to negative 0.5. Okay, so we just go look them up. Actually, we should change that to 50 and 50. Oops, what happened there? All right, let's go get the table or chart. And for the positive one, 0.5 is right here, which actually we saw this earlier. 0.6915. And then the negative version of that is 3085. I think we had that one earlier as well. And so the difference between the two is 0.3830. Okay, and again, if you're going to use your calculators, this time it's in between. We don't need to deal with infinity at all. And so we're going to have between, what are we looking at? Negative 0.03 and positive 0.27. All right, let's throw that into the calculator and see what happens. Let's see, negative 0.03. Plus 0.27. All right. 0.3830, yes. With some slight rounding differences. And that will do it. It's actually on the calculator. Let me change it. It's 294. That's close enough. All right. So it's understood that when you use the calculator, you're going to get potentially slightly different answers than the tables, because the tables do involve rounding. In other words, because you can't actually show any values that are more precise than 2 decimals or digits after the decimal point, there's going to end up being typically some small rounding differences. All right, now this last one is our normal approximation. Now, it doesn't say that, but if you look at it carefully, you're flipping the coin 1,000 times. And we're trying, X represents the number. So we declare that this is a binomial experiment. Therefore, we can compute any probabilities for X using the binomial distribution. But as you can see that would require a lot of time because there's a lot of numbers that we need. And so therefore, we probably would be better off using the normal approximation to the binomial. Although it doesn't explicitly say that, I probably should throw that in there in order to save time. So how does that work? All right, well, first of all, we know that n is 1,000, and pi, the probability of success, and again, it doesn't actually say this, but I think it should be clear that the probability of the head is 0.5. Okay, that's all we need to know. Now, in part A, first, they're asking us for the moments. To recall, for the binomial distribution, the expected value is n times pi, which in this case is 1,000 times 0.5, which is 500. The variance, which is of course sigma squared, is n pi 1 minus pi. All right, so that's going to leave us with okay, and then the standard deviation, I'll throw that in there as an equation. All right, so we'll have sigma, and we know that this is just the square root of the variance. Where are you? Ah, there you are. Okay. All right, so we're just going to take the square root of 1,000 times 0.5 times 0.5. Anyway, that works out to be about 15.81, let's say. Okay, now it's important to be able to do these, get these results, because if we're going to calculate these normal probabilities, we have to use a slightly different version of this conversion formula. Instead of this, we're going to use its equivalent version for the binomial distribution, which is expected value of x. Actually, no, sorry, it's x minus expected value of x over the standard deviation of x, which would be written as x minus n pi over the square root of n pi 1 minus pi, which in our case will be x minus 500 divided by 15.81. So the other thing we don't want to forget about is that we need to use this so-called continuity correction. So the probability of being between 480 and 520. With the continuity correction, we subtract 0.5 from the lower limit and add 0.5 to the upper limit in order to improve the approximation. And then note, we do not add or subtract from positive or negative infinity. So if one of your limits is positive or negative infinity, you don't change them, you just leave them. because it doesn't affect it. I mean, what is infinity plus a half? Well, it's still infinity. Okay. So that means here, after applying the continuity correction, we have, all right, so all I'm going to do is subtract a half from the lower limit and add a half to the upper limit. Okay, now the next step is to apply this formula. All right, hold on a second. Okay, so what we're going to end up with here is this. If we were to visualize, this is x, which is normal, or we're treating it as normal. Remember, x is really binomial, but we're treating it as if it were normal, with a mean of 500. Let me just make that a little neater. And down here, 479.5. Okay, so we're going to have the corresponding standard normal, or z-scores. I wanted this to look good. Okay, that's not too bad. So this is what we're looking for, of course, these two z-scores. And let's find out what they are. Okay, so that's x, this is z. So we can do it over here. Here we go. Okay, now here, there's always a potential here to create some rounding problems, but as long as we're careful, we should be okay. So what do we have here? 479.5 minus 500 divided by 15.81. This is approximately, well, I'm going to round this to negative 1.3. And then the one on the right, 20.5 over 1581 is approximately, yeah, it's positive 1.30. Okay. All right, so now, of course, to use the tables, we can write it like this. And then let's go look them up. They're right here. Positive 1.30 is right here. 0.9032. And then the negative of that will be, let's get these out of here. Negative 1.30 would be right here. .0968. Okay. .8064. Okay, that's our final answer. All right. Now, we could look up the exact value, but there's really no need. I'm sure it's a very close approximation, especially when the probability is a half like that. That tends to give us the best results. If you're really dying to know, let's say that it's your mission in life to understand what the actual probability was in this case. You could go into Excel. There's no, you would never want to do this with a calculator. So what do we have? We had 1,000 flips. The probability of success. All right, I think I can find this symbol editor here. Hold on. There it is. So we're looking for the probability of being between 480 and 520. So this is what you actually have to do. Actually, we can do it all directly. You literally would have to do it once for each and add them up. Oops. So the Excel function is called binom.dist. Now it needs to know a few things. The number of successes is here. The number of trials is a constant, B1. We'll use dollar signs to lock in that reference. The probability is directly below it, B2. And cumulative is no or false. You can just type in false or 0. All right, so then I will just, watch how fast this is though. A double click, it fills in the column. And then the number we're looking for is here, the sum. $80.52. So what did we get? Oh, not bad. So we'll just make a little note here. Not that you're expected to do this, but the actual probability is 0.8052. So it's understood that, you know, we're getting a slight, it's somewhat of an approximation, but it's a lot faster, obviously, than doing it directly. Now, I did mention this once before. I mean, this was very useful before people generally had access to computers or certainly laptops and Excel. So now the usefulness is not quite what it used to be, but there are cases where we can still use it. So, but it's important to understand how the binomial distribution relates to the normal distribution. If we were to actually create histograms out of these probabilities, you would see that it looks very much like the normal curve. We're not going to do that right now, but you could do that if you were interested. Just run through all the probabilities and then make a histogram, and you'd see that it does look very much like what we're seeing here. All right, now we have two more. More than 525 heads. Okay. So that's actually, oh, this one is D. More than 525.
Professor Hamilton, is there a way to do
Yeah.
a calculator?
Sorry, I can't hear you.
No problem. Is there a way to do problem D on the calculator?
Oh God, I'm glad you reminded me. Yes, I almost skipped right over it. Yes, thank you for reminding me. Absolutely. I was so busy with the Excel. Yes, let's try that. Yes, because of course that's probably what you're going to wind up doing. If you have the calculator, you might as well take advantage of it. Now, the range of possibilities here is from 479.5 up to, and that's because of the continuity correction, 520.5. The mean, remember, was 500, and the standard deviation was 1581. Now, this is a case where the difference between what we just did and what the calculator gives us could be relatively significant because there's a lot of rounding going on here. So let's try that. 479.5, 520.5. Now this time the mean is 500 and the standard deviation is 1581. And so I'm getting 8052. Oh, wow. That's interesting because that's almost exactly right, as we just saw. I think, well, again, it's because the tables, like, remember we saw that this isn't actually 130, it's 1.29 something. And I think that's what accounts for the big majority of the rounding issues. Because with the table, we're required to round it to 2 decimal places, whereas here, the calculator is using the exact values of the Z table. So that's why it's so much closer to the true probability. Interesting. So anyway, but either way, whatever you do on the test, this is fine. Both approaches are fine, but remember, it's understood that this is an approximation anyway. All right. So now, in this case, what we've actually got here is this. We could think of this as the probability that X is somewhere between 525 and infinity. Okay. Now, we're going to apply the continuity correction, but only to this number right here. Now, in principle, we only have 1,000 flips. And you might say, well, why don't we just use 1,000? And we could, but the thing is, when we're using the normal distribution, we're going all the way up to infinity. Plus, the probability of getting 1,000 is so minute that either of these two will give you an answer which is so similar that it would probably be several zeros past the decimal point difference between the two. So we're going to just stick with this approach. 1,000 will be replaced with infinity, because as far as the normal curve is concerned, that's such a large number, it may as well be infinity. Okay, so anyway, so what we're going to do is use the continuity correction. And we're going to replace this with and remember, the lower limit needs to be reduced in order to improve the approximation. Okay, so let's apply the formula. Z equals X minus 500 over 1581. All right, so now this becomes this. All right, and this is going to be approximately, let's see, 24.5 minus, 24.5 divided by 1581. It's approximately 1.55. It's not exactly, but it's close enough. So you're basically looking for, under the normal curve, okay, that's what we're aiming for. Now, of course, on our charts, we don't have this probability. We have to rewrite this as 1 minus the probability that z is less than or equal to 1.55, which we can easily look up now. Let's go to that table. 1.55 would be the intersection of 1.5 and 0.05, 93.94. So this is obviously a very small probability, 0.0606. Okay. All right, so now what about the calculator? Our old friend, the calculator, yes. Let's try this. So this, in this case, the lower limit was 524.5. The upper limit, we'll make that infinity. And let's see what we get. Okay, let's try that. $524.5 up to infinity should be 0.0606. Oh, they're pretty close this time. Very nice. Awfully close. Okay. And then there's one more, a less than or equal to case, which is 485. Okay. It's F, isn't it? Yeah, that's F. 485. Okay, so using the continuity correction, this becomes, so basically what we're doing is treating this as okay, we're going to add to, that's the upper limit. So we're going to add to that, and then we're going to apply our formula. Okay. Therefore, this equals okay. Negative, let's say 0.92. All right, well, you know what? We can look this up directly in the charts. Let's do that. And we'll go to the negative chart, negative 0.92. Okay, at the intersection of negative 0.9. This is actually 0.02. It's hard to see, but there it is, 0.02. The third column is 0.02. So we have 1788. Beautiful. And then with the calculator, we should get something very, very similar. We're going to go from negative infinity up to 485.5 with the same details, the same mean, same standard deviation. And now let's see what that gives us. $17.95. Ooh, that one's off a bit. I wonder why it's so much. Yeah, that's a little surprising. The other one was so close. This one, not quite, but all right, that's what it is. And of course, neither one of them is exactly correct. For that, we need to go back to Excel and fill in that column in Excel, and we can get the exact numbers. So anyway, so that's that. Now this is done. I'll post this one. I called it sample midterm 2 with remaining solutions, because here we only needed to do the last two problems, 6 and 7. The rest we did yesterday. So you'll have a complete set. The midterm is actually already on the Moodle, so you can start it like even as soon as we're done here if you want to. And so then what remains to be done here is we need to go back and revisit chapter 9. I want to review it quickly, but also I want to show you some calculator shortcuts as well. And then we're going to dive into the appendix where we look at confidence intervals, not for the mean, but for the proportion. And then if there's any time left, we'll at least take a peek at chapter 10, which is the actual last chapter of the course. It's like the normal distribution. It's something that you'll see continuously when you get, if you get into a more advanced statistics class. Okay, it's awfully, awfully important. It's called hypothesis testing. Now, we all know what a hypothesis is, but we're going to see that there's a formal procedure here which enables us to draw conclusions from a population, but we're not ready for it just yet. So in the meantime, since it's just after 11, why don't we stop right here and have our morning break? And when we get back, we'll carry on with 9. And if there's time, we'll take a peek at 10. Okay? All right. See you all in a bit. All right. Here we go. So, chapter 9. So we were actually done with it all except the appendix, but I still wanted to show you one key detail, and that would be the shortcuts on the calculator. Yes, now this was a very complex process, calculating these confidence intervals. But there's good news. There's a quicker way of doing this with the calculator. So first, let's quickly remind ourselves what exactly we were doing. We were constructing confidence intervals for a population mean. And of course, all confidence intervals are constructed from a point estimate of some kind, plus or minus a margin of error. So for population means, the point estimate that we use is the sample mean, and then the margin of error depends on whether or not we know the population standard deviation. So we have two basic cases here. The first case is where the sigma or population mean is known. And when that happens, we have this as our confidence interval. We start with our sample mean, and we add and subtract these terms on the right. This Z is a Z-score based on whether you're using a, let's say, 95% confidence interval or 98 or 99, whatever. And then this is the population standard deviation. And of course, this is the square root of the sample size. So in our examples, we saw that in each case, what really is only changing from one confidence interval to the next is this Z-score. So let's say, for example, and we went through and did some calculations here, but what we really want to do is do an example from start to finish. Let's say that we have a hedge fund. Here it is, the hedge fund. It has a portfolio which consists of 500 stocks. The annual rate of return among these stocks is normal. The standard deviation is known at 0.20, so we're going to use the normal distribution. We have a sample size of 10, and in that sample, we find that the mean is 8%. So we're going to use this information to construct three different confidence intervals for the true population mean, 90, 95, and 99. All right, so now remember, we need for each of these three cases to construct not only the sample mean, which we know, but the margin of error. So what we're aiming for is, let's just remind ourselves, the margin of error is Z alpha over 2, it's called, sigma over radical n. So the alpha over 2 comes from the confidence level, as we call it. So in other words, if we want to construct a 90% confidence interval, we say that the confidence level is 90%. In other words, that's how confident we are in our results. I guess you could think of it that way. Confidence level is 90%. The alpha is therefore 0.10. Okay, in other words, the confidence level is basically 1 minus the alpha. So to have a 90% confidence level, that implies that alpha is 0.10. Now that in turn means that our confidence interval covers the area between these two tails. 90% of the distribution falls between plus or minus 1.645. The remaining 10% is split up evenly between the two tails. So that means that the appropriate Z-score here is 1.645. And of course, this is the negative of that. So we looked this up in our calculators under the INV norm function. It's here somewhere. I've forgotten exactly where we explained that. But okay, well, here's a list just to remind you, because there's really, these are the three most commonly used confidence intervals, 99, 95, and 90. So once you know these Z-scores, you don't have to continuously look them up. You can write them down, you can make a chart. But the function that we use to come up with these numbers is called INV norm on the calculator. Here it is. This is where we originally figured out that with a 90% confidence interval, we were going to have a Z-score of 1.645 because the entire right tail area is 5%. Everything below that has a probability or area of 95%. So the proper Z-score is 1.645. For 90%, it was 1.28. And then I think we also did 19. Oh, all right. Well, we did eventually do 99%. And that turned out to be 2.576. All right. Now, with all this information in front of us, we were able to now construct our confidence intervals. We started with 90 rather, and you plug in all the numbers that you have, including the z-score for 90%, and you end up with this interval. Okay, well, that wasn't too painful. For the 95% confidence interval, we just replaced this z-score with 1.96, as it turns out. Okay, and then for 99%, we replaced the z-score with 2.576, and so we have these as our three intervals. Now, you're probably wondering, isn't there a nice way of doing this on the calculator? And the answer is yes, of course. The calculators can do almost anything you could imagine. Not everything, but many things that will save us a lot of time. So what I'm going to do here is put in a slide here that explains how to do the same procedure with the calculator. So this way, if you have it, I mean, that's fine. You can use this. If not, you can use the traditional approach. So what are we looking for? Okay, so constructing confidence intervals with the calculator. And of course, when I say the calculator, I mean the Texas Instruments. Whichever one you happen to have should do the job. But the TI-83 and 84, I think, are the most commonly used ones for this. So here's what you need to do. So you're going to go to your stat menu. Let's start by mentioning to construct a confidence interval for the population mean when the population, well, just in general. Here's what you're going to do. Hit the stats button. Stat. Now, you do have to make a decision here. You have to know which technique to choose from. Oh, you have to go to the test menu. Stat tests. Okay. Once you get there, you have to decide what you need. Now, the key to the whole thing is that these are confidence intervals. And because you know the population standard deviation, you're going to use Z interval. Okay, Z interval. So actually, let me change this a little. To construct a confidence interval for the population mean when the population standard deviation is known, this is what you have to do. And you choose Z interval. And guess what it's going to do? It's going to ask you for the information you have. Now, here, there's another decision you have to make. Now, we didn't do any examples where we had the original data. If we know the original data, we can use the data menu to tell the calculator where the data is stored. Okay, but we haven't done that. If not, we use the stats menu. Okay, so in our examples here, we would then use the stats menu. We do not know the actual data. All we know is the mean and the standard deviation. Okay, so we go to the stats menu. And when you do that, it's going to ask you for several key pieces of information. And you're going to type them in. Okay, so the calculator requires following information. Okay, it starts out with sigma, if you notice, on the top. And so in our example, if we go back and remind ourselves, the standard deviation was 0.20. And then it needs to know X bar, which I will just write as X bar. There's no symbol for that. X bar was 0.08. Okay. And then it needs to know N. Oops, hold on. N. In this example, N was 10. And then we have something called C level. Now, C level is just shorthand for confidence level. Let's start with 0.90. So I'll make a note here, 90% confidence interval. And then, of course, you just hit the calculate button. All right, so let's just go through this. 0.2, 0.08, 10, 0.9. And let's see what it comes up with. So it comes up with on my calculator, the interval negative 0.24 and one, and the my calculator at least 0.18403. Okay. Now, when we did this, the results were, so you're going to see that it's virtually identical right here. So except for the most trivial rounding differences, we got the same results. Okay, so now in order to obtain or calculate 95% and 99% confidence intervals with the same data, we just have to change the value of C level for each individual case. Okay, so in other words, you can get all three of them very quickly by simply changing the C level. Once you have the basic data put in there, it's just a question of changing the C levels. So that's how it's done on this calculator. You can see it does save you a lot of time because the traditional way, there's a lot of steps involved. You have to look up a lot of information. You have to go through a lot, let's just say. All right, well, now, what about the cases where the population standard deviation is not known? All right, so remember, in that case, we're using the so-called t-distribution. That's the only difference. The basic setup is the same. Let's jump ahead and look at the formula. And of course, we spend a lot of time analyzing the t-distribution, which is important because we need to understand what it's doing. But let's skip ahead and we'll look at, here we go. Sigma is unknown. So the only real difference here is that you're assuming that you do not know the population standard deviation. So you replace sigma with S, and the t-distribution is used now instead of the standard normal. Now, what we're going to do then is try this example with our calculator. So let me copy these now. So because they're the same, except for that one little change. Hold on a second. Here we go. So I'm just going to steal this and use it again. Here we go, right there. Okay, so when the standard deviation is unknown, we're still going to use stat, but guess what? Now we're going to use t-interval. All right, if you go back to that menu, stat tests, you'll see directly below z-interval is t-interval. And then you'll go to the stats menu again. Okay, because we don't have the original data. Now this time, you'll notice it's set up a little differently. I don't know why they did that, but it's organized a little differently. We have X bar, then we have this thing SX, it's called. That is sample standard deviation. Just in case it wasn't obvious, that little x is, some books use it, some don't. And then you need to know the n and the sea level. Now, in this particular example that we're using with the t distribution, let's go back and revisit the data. We were told that the mean was 3.10 and the standard deviation was 0.25. Okay, now what about the sample size? Let's go check that out. The sample size was 10. Oh, it's still 10. All right. So why don't we do the 90% confidence interval using this information, and then we'll compare it to what we got with the actual traditional approach. So let's plug these into t interval, 3.10 for x bar. The standard deviation is 0.25, n is 10, sea level is 9. Let's do the calculations. And we get 2.9551 up to 3.2449. And when we did this ourselves, we got, there we go. So you can see it's virtually identical. And again, you can now go ahead and do the 95% and the 99% for the same problem, and you'll end up with the correct results. All right, so now you're all relieved to discover that all of that work isn't absolutely necessary, but you do have to understand what's going on behind the scenes. So it's helpful to see how this is done in the first place before you can lean on any shortcuts in your calculator. Okay, so, well, that was good. Good practice. Now, that concludes our discussion about confidence intervals for the population mean, but we have one more step in this chapter. We're going to look at confidence intervals for population proportions. Okay, so we haven't seen that before. And so let's do that now. I put all that information in the appendix because some years we run out of time and we don't cover this material. That's why it's in the appendix. So I think I opened that already. Here it is. Okay, so now we're going to construct a confidence interval for a population proportion. Now, a proportion, as the name sounds, it's really just a ratio. So in other words, if I told you that, let's say 60% of the population lives in cities, then the proportion is 60%. 0.6 or 60% of the people in the US live in cities as opposed to the suburbs or the rural areas. So a proportion is simply a ratio of the number of people with a certain characteristic to the total population. Like, for example, I could ask in our class, what proportion, I think we did this the other day, what proportion are left-handed? And it turned out to be, I think it was 2 out of 15 or something like that. So what we're going to do, though, is construct a confidence interval for the population proportion, which obviously we don't actually know. So instead, we have to resort to either coming up with a sample, a point estimate, like the sample proportion, or else construct a confidence interval. So what exactly are these symbols telling us? All right, well, first of all, let me add a few details here. Based on that formula, P equals the sample proportion. Okay. N is the sample size. Now, we're also going to use the letter X, which we don't see here. X is the number of elements in our sample with a specific characteristic so that P actually equals X over N. All right, so let me give you a quick example of this. suppose that, let's think of a fun example. Suppose that Breyers wants to determine what proportion of the population prefers chocolate ice cream to vanilla. Now, if they had the population number, none of this would be absolutely necessary. They're trying to figure out how much of each to make. You know, in their factories, they're making both vanilla and chocolate. They want to know what proportion should they make for chocolate and what proportion for vanilla. Okay, so a sample of, let's say, 450 customers is chosen and 382 prefer chocolate. Therefore, the sample proportion is, so it's a pretty simple idea. So the X is the 382, the sample size is 450, and that gives me approximately almost exactly 85. It's like 84, 89. Roughly 85% prefer the chocolate to the vanilla. Now, that is a point estimate, by the way. It does not take into account the amount of uncertainty that we're likely to get from one sample to the next. So that's why we may also want to construct a confidence interval to get a better feel for what's the range of possibilities here. So that's what this is for. Now you notice there is a z-score here like we had in the previous section. Here's some good news for you to make things simple. Let me add this as a little note here. Oh, looks like I had another example lined up for you. Suppose that a random sample of 105 fast food restaurants is chosen. Of these, 74 offer at least one vegetarian option. So the sample proportion is 0.7048, okay? Not a problem. So here's an interesting result. I guess where should I sneak this in here? Anywhere will do. Let's see, hold on. Want to make things everything nice and tidy. There we go. But what I wanted to mention here is that before I do our example, when constructing confidence intervals for the population proportion, we always use the standard normal distribution. Okay, in other words, in this section, we will never use the t-distribution. As soon as you see that you're dealing with a population proportion, that means you automatically use the standard normal distribution. Okay, so there's only that one option. And that should make things a little bit simpler. So you don't have to make any decisions. As soon as you're asked to construct a confidence interval for proportions, this is the formula you'll use. Hands down, there's no getting around it. Okay, now let's do an example of that formula we just saw. Oh, this is for the fast food example, by the way. So again, we were trying to find out what proportion of fast food restaurants have at least one vegetarian option. And the sample proportion was 0.7048. Now we're actually going to go ahead and construct a confidence interval. All right. So now this part we're familiar with. The z-scores haven't changed. For 90%, we'll use 1.645. For 95%, we'll still use 1.96. And for 99%, we're still using 2.576. All right, with that part taken care of, now it's just a question of plugging everything into the formula. Okay, so P we know to be 0.7048. That's a sample proportion who do offer a vegetarian option. This is our z-score. Here we have P1 minus P, the sample size. So you plug all those into your calculator. And it's a bit of a mess, but you can plug this into your calculator and you're going to get your result. Okay, now of course this term on the right-hand side, as usual, is the margin of error. That doesn't change. And this is our point estimate. This is always the way we construct confidence intervals, a point estimate plus and minus the margin of error. All right, so let's see what this turns out to be. So you plug everything in and you get a range between roughly 61.76% and 79.20%. This is our 95. Oh, wait a minute. I think I jumped ahead to the wrong page. Hold on a second. Sorry, this is 90 right here. This is 90%. You can tell because the z-score is right here. Okay, so the margin of error is 0.0732. We're adding, subtracting that from the sample proportion to come up with this interval. So while this is our best guess of the population proportion, we know that there's a 90% chance that it's actually in here somewhere. And that's the purpose of confidence intervals, to give us some sense of how much uncertainty there is. This is our measure of uncertainty, by the way. We're basically saying that we think it's about 70.48%, give or take about 7.32%. That's essentially what we're saying here. Beautiful. Now, to do 95%, we only need to make one change. That's the z-score. This is exactly what happened in the previous section. So all of a sudden, the 1.96 is here, and this is our new result. Okay, so the number under the square root sign will never change. That's 0.0445. So literally, we're only changing this z-score as we go through the different combinations, 90, 95, 99. And when we raise the z-score, of course, we raise the margin of error. So in order to be more confident, we have to have a wider confidence interval. And that's exactly what we have. All right, so you can probably guess what's coming next. To do 99%, we're going to replace the z-score with 2.576. And that will give us an even wider interval because the margin of error will go up even further. Okay, so let's see what that looks like. The z-score there is 2.576. Again, what's under the square root sign doesn't change. Here's our brand new, our higher z-score. This is the new margin of error. And there it is. All right, now what I'd like to do is, just like I've done before, I'd like to have a summary of all of them together in one place, just so you can see them all together. All right, so for 90, we wound up here. %, oops, 95 is here. And then finally we'll have 99 right here. And again, the idea is you can see very quickly at a glance that the higher the confidence level, the wider the interval has to be, because it has to cover more possibilities. All right, now this time, unlike the last chapter, I actually have included in the slides the discussion about how to do this on your calculator. Now, We're going to go back to the stat menu, and you're going to look at the tests, stat tests. And now this time, remember, I did say that with proportions, you're never going to use the t-test. So what you're looking for is called the one prop z-test, which means one proportion z interval. You're only considering one proportion. Once you get there, let's see, and it's pretty far down. It's on letter A in my calculator. It only needs 3 numbers, which is kind of nice. It needs X. Remember, way back, we saw that we had a sample of 105 fast food restaurants, of which 74 do have a vegetarian option. So it's 74 out of 105. Then you tell it which confidence interval you want, or confidence level rather, and it magically does the rest for you. Okay, so, okay, so what do we get? It should be the same. So on my calculator, I've got 0.63154 up to 0.77798 using the formula. We obtain the result. We just want to see how close they are to each other. So this is our 90% confidence interval. So again, it's virtually identical. It's not absolutely identical. There is some rounding going on here, but this is how it's done. And then, of course, just like before, we saw that what you can do to get the other confidence levels is literally just go back to your calculator and change the C level. The rest can stay the same. So you can get all 3 of them very, very quickly and easily. All right, so you can use the formula if you want to, but if you have this calculator, you may as well take advantage of it, because you can see it's saving us a lot of time, but you still are expected to understand what the calculator is doing. All right, don't just say, well, it gave me that number, it must be right. You have to know what's going on, because otherwise it would be easy to make a lot of mistakes. That's exactly the opposite of what we want. Okay. Now, there's one more case that I want to look at, but I don't want to rush through it. We also want to consider the case where we're comparing the proportions of 2 samples taken from 2 populations. That is our last confidence interval in this chapter. And when that's done, you can see, whoa, look at that formula. When we're done with that, then we can dive into chapter 10, the final chapter of the course. Now, 10 is a fairly complicated chapter, as you can imagine. So that's going to take us a while to get through it. Luckily, we have the rest of this week, and we have 2 days next week that we can meet. And no matter what happens, though, at some point we have to review for the sample final, which is on 8, 9, and 10 only. It's not comprehensive. It's 8, 9, and 10 only. So what we've been doing the last couple of days will be the content of our final exam. So we'll finish this one tomorrow. It won't take that long. We'll dive into 10. And 10 is, let's just say 10 is one of these topics where it requires a lot of background explanation before we can actually do the examples. But it ties in nicely with everything we've been doing up to this point. It does not require any new probability distributions. Every time we'll either use the T or the Z. And when it's done, you'll say, oh, that was interesting. It's basically an alternative way of trying to get results which help us understand what's going on with the underlying population. So in a lot of ways, what we're doing in chapter 10 is simply an equivalent way of getting at the information we're finding in chapter 9. But it has a lot of uses and a lot of applications. And so that's why I said a lot of this stuff, you'll see it over and over again if you do find yourself in a more advanced stats class, which could happen if you decide to major in economics or business one of these days. All right, so I guess we'll knock it off here, unless there's any last minute questions. I'll be posting the rest of the answers to the sample midterm, so you have all of them right in front of you when you're doing your work. And other than that, I guess we're done. All right. Any questions?
Thank you, Professor.
Okay, you're welcome. See you next time, tomorrow.
Professor, I have a question.
What is it?
Did you receive my homework last night by any chance?
Okay, let me see. I'm gonna look on here and I can probably tell our boss. I don't know offhand. I'll double check. You mean you handed in chapter 6 and 7 last night?
Yeah.
All right.
The issue is like those files, like when I take a photo of them, when I send them to you, they're too big. So I do it off like I do it like off like a PDF like file.
I
So
see.
so sometimes it like makes it like a lot wider than it really is.
Oh, I see. All right. So far, it hasn't been a problem, but as long as it's something is in my inbox, that's fine. You know,
Yeah,
and
of
if I can't read it, I'll let you know. But I mean, I don't remember specifically seeing it, but I'll let you know if I can't read it or find it.
Okay, yeah, and just to clarify, Wednesday is when that midterm. It's Wednesday at
The
midnight. Wednesday morning.
Wednesday midnight.
All right, perfect. Thank you so much.
I just feel like why not? If it's still Wednesday, isn't it? At 11:59:59.
Yeah.
So therefore, if I say Wednesday, I must include everything up until midnight, right?
I believe so. Yeah.
Okay, there you go. So all right, yeah, Wednesday at midnight is fine. So I decided to give everybody extra time because I figure, you know, you had a lot of assignments this weekend.
Yeah, I honestly, I really did need it. So thank you so much.
Okay, you're welcome. All right, good. So I'll see you tomorrow then.
Yep, I'll see you tomorrow. Thank you.
All right. Anyone else? Okay, good. And I'll see you all tomorrow.